Hello, welcome back to Discrete Calculus with the Wolfram Language. I'm Alistair Forsyth, and this lesson will be all about partitions. To get started, the word partition can mean slightly different things in different contexts. For example, a partition of an integer n is a specific representation of n as a sum of positive integers. A specific ordering of an integer partition is called a composition. On the other hand, a partition of a set is a set of subsets of that original set that are non-empty, non-overlapping, and whose union is the original set. For example, 1, 2, 3, 4 is a partition of the set 1, 2, 3, 4 because none of those sets have anything in common, none of them are empty, and the union of 1, 2, 3, and 4 is 1, 2, 3, 4. Finally, a partition of an interval is a set of strictly increasing elements, with the first and last values being the start and the end of the interval. For example, a partition of the interval 1 to 5 could be 1, 2, 3, 4, 5. Now, there are some specific functions that are commonly used when talking about partitions, like the partition function p of n, which returns the number of possible partitions of a positive integer n. For example, p of 3 is equal to 3, as you can write 3 as 1 plus 2, or 1 plus 1 plus 1, or 3. On the other hand, the partition function q of n returns the number of partitions with distinct parts of a positive integer n. For example, q of 3 is equal to 2, because we can rearrange 3 as 1 plus 2, or 1 plus 1 plus 1, or 3. However, 1 plus 1 plus 1 has 1 repeating. Therefore, we can only write 3 with distinct parts as 1 plus 2, or 3, so q of 3 is 2. When the order that we put a partition into matters, we can look at the number of compositions of an integer n into k parts, which will be equal to the binomial of n minus 1, k minus 1. Now, this type of composition of an integer into exactly k parts will be known as a k-composition. Using this formula for the number of k-compositions of an integer n, we can use the Wolfram language to figure out a formula for the number of any type of composition of a specific integer n. To do this, we'll just take the sum of the number of k-compositions of an integer n as k moves from 1 to n. We can define n as our upper bound for the specific k value, as any different composition of an integer n can never have more than n parts. So, plugging this into the Wolfram language, it returns us 2 to the power of n minus 1. Now, taking more of these functions in the Wolfram language specifically, we have partitions p of n and partitions q of n, which function as the p of n and q of n for integers. Plugging in partitions p of 5 and partitions q of 5, we get 7 and 3. Now, this makes sense because you can write 5 as 1 plus 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 3, or 1 plus 1 plus 1 plus 2, or 1 plus 4, or 1 plus 2 plus 2, or 2 plus 3, or 5. However, out of those partitions of 5, only 1 plus 4, 2 plus 3, and 5 have distinct parts, so partitions q of 5 is going to be 3. Along with that, we have the function integer partitions of n, which returns a list of all possible partitions of n. If we evaluate integer partitions of 5 in the Wolfram language, we get 5, 4 plus 1, 2 plus 3, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1, which I probably should have listed out before I just spoke all of them a moment ago. Moving on from that little blunder, we have partition of a set and an integer n, which returns a partition of the set into subsets of a specific length n. If we give the Wolfram language partition of 1, 2, 3, 4, comma 2, it'll return 1, 2, 3, 4. Now, this makes sense because both of those sets are non-overlapping and neither of them are 0, and their union is 1, 2, 3, 4. Outside of our computational tools, we also have ways to graphically visualize different partitions. For example, here we have a Ferrers diagram for a partition of 100, which I got from Wolfram Math World. You see, the way you read these is that the nth row of dots represents the value of the nth part of a given partition. So using that rule, we can go through each of these rows, see that the first has 21, the second has 17, then 13, 10, 5, 4, 4, 4, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, 1, and the final row has 1. Now, if we put these all together and use the Wolfram language as just a little calculator, we get 100. So we can tell that this partition is accurate. Moving on, we have a particular property of partitions, namely Ramanujan's congruences, which give us more insight into how P of n acts for certain values of n. In 1919, the mathematician Srinivasa Ramanujan showed that the following congruences hold true for the partition function P. He said P of 5k plus 4 is congruent to 0 mod 5, P of 7k plus 5 is congruent to 0 mod 7, and P of 11k plus 6 is congruent to 0 mod 11. Now, using the mod function that we went over in our modular arithmetic video and the partitions P function, we can write some code in the Wolfram language and show that each of these congruences hold true. Note that the numbers I used, 24 is 5 times 4 plus 4, 19 is 7 times 2 plus 5, and 28 is 11 times 2 plus 6. Along with that, we also have a sequence of numbers called the Bell numbers, which act like P of n for the partitions of a set. More specifically, the nth Bell number, B sub n, represents the number of partitions of a set of length n. To demonstrate this, we'll bring in our combinatoria section of Mathematica and use from it the set partitions of n function. Now what this will do is take all of the different partitions of a set of integers 1 to n. So if we take set partitions of 4, we'll get the set 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 3, 4, 2, and so on and so forth. Now if we take the length of this as n goes from 1 to 10, we get 1, 2, 5, 15, 52, 203, 877, 4,140, and so on and so forth. Now if we use the function Bell B of n in the Wolfram language to write out the first 10 Bell numbers, we see that it gives us the same sequence, which shows us kind of where the motivation for Bell numbers comes from. Moving into some applications of partitions, we can see equivalence classes come up. The set of all equivalence classes on a given set is actually a partition of that set. For example, we can partition the positive integers into the equivalence class of 1, the equivalence class of 2, and the equivalence class of 3 when taken mod 3. This divides the positive integers into 1, 4, 7, and so on and so forth, and then a set of 2, 5, 8, and so on and so forth, and then 3, 6, 9, and so on and so forth. Now we know these are non-overlapping because no positive integer can be congruent to both 1 and 2, or 2 and 3, or 1 and 3 when taken mod 3. And of course we know that none of these sets are empty because we know that, 1 will be in the first one and 2 will be in the second, and so on and so forth. And finally, we know the union of this set will be the positive integers because every positive integer will have to be congruent to 1, 2, or 3 when taken mod 3. Moving on to partitions of intervals, our most common use for them is to describe the bounds of a Riemann sum. Take this piece of code written in the Wolfram language. We plot a simple function and then create a midpoint Riemann sum. To do this, the Wolfram language has to partition the interval 0 to 4 into 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and then 4. Now this process is extremely variable, but really important because every time you make a Riemann sum for any function, whether it's a left point approximation, a triangle sum, a right point approximation, or a midpoint approximation, to create that approximation, you have to partition the interval over which you're estimating the integral for. Anyway, moving on to partitions of sets, we can use them to analyze rhyme schemes. If we take a poem with n lines and create groups based on which lines rhyme with each other, it will end up being a partition of the set of lines. You see, no given line can rhyme with two other lines that don't rhyme with each other, so the groups can't overlap. Along with that, each line will rhyme with itself, so all lines will be in a group and no group will have no lines. Now this implies that the number of possible rhyme schemes for a specific length poem will be equal to the Bell number associated with its length. Moving on to my favorite thing in this presentation, we can use integer partitions of n, 1, 2 to show an identity that we learned in the lesson on Fibonacci numbers. Now this piece of code is hard to digest, but it'll make more sense if we go through each individual bit. First, what we do is we take integer partitions of 4, 1, 2, which then lists out every possible integer partition of 4, except only using the numbers 1 and 2. Then we use the permutations of n function on each of those partitions to get each different ordering of those partitions, giving us the total number of compositions. We then join each of those permutations to get a full set of the number of compositions of 4 using only 1 and 2, and then we finally take the length of that. Evaluating this, it gives us 5. Now that's not that interesting in and of itself. However, if we take a table of that piece of code, except with 4 as n minus 1, and n going from 2 to 14, then we can see a bit of a pattern start to arise. We get 1, 1, 2, 3, 5, 8, 13, and so on and so forth, which is really cool because we just found the Fibonacci numbers using only integer partitions. Now, if you haven't seen our lesson on Fibonacci numbers or you don't remember, what this is basically showing is that f sub n, the nth Fibonacci number, is actually the number of ways you can describe n minus 1 using only 1 and 2 as addends. I think my favorite things in different math problems is when something appears completely out of nowhere, or not out of nowhere, but in a way that's not specifically intuitive. So it's really cool to me that we can pull the Fibonacci sequence out of just different integer partitions and different permutations of those partitions. Anyway, in this lesson, we covered partitions of integers, partitions of sets, and partitions of intervals. We covered compositions and Bell numbers, and we went over some applications of each different concept here. In the next lesson, we're going to look at another sequence in particular, specifically the Bernoulli numbers. I'm Alistair Forsyth, and thank you for watching. Bye-bye.